the previous lecture, we have discussed how an given switching equation can be reduced using Boolean algebra. Moving further, in this particular class, I'll be discussing how an given switching equation can be converted into an logic diagram. So, as per the previous discussions, when we go for converting any switching function into a logic diagram, the procedure that has to be adopted is as follows. First, consider the given equation and see that equation can be simplified using comparison method to minimal equation. Once the minimal equation we derive, finally we can construct the logic diagram. So to illustrate this process, let us consider few examples, and from the examples or from the given switching functions, we will see how we will construct the logic diagrams. In order to illustrate, let us consider a equation or a switching equation as G equal to x bar, y bar, z bar, odd with x, y bar, z, odd with x bar, y, z bar, odd with x, y, z. In order to construct this particular logic diagram, the very first step that we need to adopt on this given equation, logical switching equation, is that using comparison method, remove the redundancy if it is within the terms. So for which, first what we'll do, we will be applying the reduction or comparison method to remove the redundancy amongst the terms. When we start applying the process, we have to identify the various terms in the equation, that is within the switching equation. If the terms have been represented, so you can see that there are 4 terms. So using the comparison method, we have to identify the redundant terms, and we have to apply the Boolean laws, and we have to remove it. So therefore, first step is to apply the comparison method. So when the comparison method has been applied, you have to compare the terms with the subsequent terms. So let me consider the term 1. When term 1 is considered, compare with the second term, term 2, term 3, and term 4, and so on until all the terms have been covered up. When the term 1 and 2, it has been compared x bar, y bar, z bar, and the second term is x, y bar, z. Here there is no single variable which is differed in between these two terms. Hence, it is not possible to remove redundancy. So therefore, not possible to remove the redundancy. So let us now take terms 1 and 2. Compare terms 1 and 3. When 1 and 3 has been compared, x bar, y bar, z bar, x bar, y, z bar. So here we can observe that there is one redundant term which can be removed. So hence x bar, z bar between 1 and 3, x bar, z bar is common variable, whereas y bar and y is a different variable, are the complement terms. So therefore, we can apply the Boolean laws, which is giving us a result as x bar, z bar, because y bar with y, when it is odd, always the output will be 1. Similarly, we need to compare term 1 and from terms 1 and 4. X bar, y bar, z bar with x, y, z. So here the redundancy it is not able to remove because all the variables are conjugate to each other. So therefore single variable it is not existing. So therefore it is not possible. In the second stage of comparison method, we have to go for second term comparing with the subsequent terms. So second term from 2 and 3. So is it possible for us to remove any redundancy? You have an x, y bar, z and x, y, z bar which are to be odd. So therefore, if you are closely observing, not possible with the removal of any variable. So therefore, we will leave as it is. Again, the next comparison is by comparing term 2 and 4. Even here, we can see that x, y bar, z odd with x, y, z. If you look at here, you can see that x is z, it is common, whereas y bar and odd with y can be applied with the Boolean law. So therefore, output will be x z. And the last stage of reduction should be comparing out of 4 terms, 3 and 4 terms compared. In the comparison, x bar, y, z bar, x, y, z. So here two variables are changing. So therefore it is not possible for us to further remove. So hence what you can do, what will be the final result? Our final expression will be the reduced expression. From the comparison results, we have x bar, z bar, odd with x z. So again, you can see whether further we are able to remove the redundancy. It is not possible because all are conjugated to each other. So hence, this will be the final expression or the optimized expression that we have. For this final result, we need to construct the logic diagram. So as we already know that the logic diagram is a diagram which will be represented through the combination of the logic gates. So when you look at here G is an output, and this output it is due to the two product terms. One product term is x bar z bar and the other product term is x z. So when you go for this logic diagram for the optimized result, so how many variables we have in the final expression? Please consider x z. And so from x, how can we get x bar? That is by using a NOT gate. X bar, z bar, and it with will provide an one product term. It is x bar z. So another term is x and z. So we can have an AND gate, and so these are the two product terms. From these two product terms, we need to get the final output, that is G. This G is equal to the ORing of these two terms, hence a OR gate. So this will be an logic representation for the minimize expression which we have got from the for the G. This particular diagram can also be represented in another way, as instead of using this NOT gate, directly we can go for X bar, Z bar, and it. So that represents that whatever the X we will be having as a variable whose complement to get, we have to connect an inverter. And another product term, it is due to the X and Z, only two variables, but those two variables which are producing different product terms. So those product terms needs to be added. So this is the logic diagram. Suppose the logic diagram, which I don't want to represent in terms of the simplified expression. The regular expression, which is in the form of unsimplified, that is directly the switching equation. If it has to be represented, how do we represent? So for that, you can take all the terms X bar, Y bar, Z bar. So that is this equation 1. For equation 1, if a logic diagram, it has been constructed X bar, Y bar, Z bar, and it, because that is a product term, or it is because X, Y, Z only three variables, you can term this as also a min term. The next product term is X, Y bar, Z, that has to be connected to an AND gate because it has to produce an product term X bar, Y, Z bar, another min term which has to be connected to an AND gate. The another term is X, Y, Z. So this also has to be connected to an AND gate. Final output G, because G is a function which is output is the result of all the four terms ORing. So hence we will be going for all the four terms ORing. So hence your output expression G will be equal to the OR of all the four terms. So this is an unoptimized circuit what we'll be having. And if the optimized circuit, if we have to derive, then this will be the logic diagram that you can take it for the consideration of any logic diagram after simplifying the given switching equation.